Hello and welcome to the day 4 of the 6th week of the lecture series. So, we have learned about the SLCs, how to form the SLCs using projection operator. So now the question is like what we will do with this SLCs. Okay, what information that this symmetry constraint toward the linear combination of atomic orbitals will give us. So now, in case of this chemical bonding or bond formation, so the valence band theory that was put forward by Slater or Pauling and many others, they considered this a bond to be it's like a two-centered bond. So the interaction between the atomic orbitals of two atoms in a molecule will make the wave function localized between the within the bond. But when the molecular orbital theory came into the existence, then that gave much more freedom, because in valence band theory it didn't consider any kind of interaction between two bonds that are formed. Okay, so in molecular orbital theory we have this idea that the wave functions for any molecular orbital, they extend up to the whole all over the molecule. Okay, so essentially you can feel the presence of the orbitals all over the molecule. So that in one sense it's helpful for us, because in that case we can actually use the the rules that are symmetry adapted. And what that will help us, in solving for various problems, including the energy of the orbitals or the occupancy of the orbitals or the bond orders, all these things, without going into detailed or hardcore computation. Okay, so in one way we can save a lot of time, and without doing too much of work we can say about the energies of molecule. Okay, how will it be, energies of the orbitals and all. Okay, and certain rules associated with this will help us in assigning different particles, meaning different say different wave functions to different molecular orbitals. Now one of the the most commonest approach to reduce the notion of an molecular orbital in an explicit and practical form is the approach of linear combination of atomic orbital. In short, LCAO. We what we approximate that each atomic orbitals they can combine in a linear fashion, and they ultimately give us the molecular orbital. So all the this combined orbitals, they are spread over all the molecules. It seems they are quite delocalized. So this is an approximation, and here we write a molecular orbital as the linear combination of the atomic orbitals, which is clear from its name. And how do we do that? So if we have the wave function for the atomic orbital, ith atomic orbital in a molecule as phi I, and psi k is the kth molecular orbital, then I can express psi k in terms of the all phi i's, right, with a particular coefficient which is denoted as Cik. So this particular combination is nothing but a linear combination, right? Now this phi i's are the that they represent the atomic wave function or atomic orbitals here. So this act as the basis function. So all the atomic orbitals, that is the complete set of the phi i's, act as the basis set. Okay, and we always would like to work with an orthonormal basis function. So set of orthonormal functions as my basis. So therefore this phi i's are written in such a way that they are normalized. All right, and any two atomic orbitals, so atomic wave functions, they form the basis of irreducible representations, and automatically they will become orthogonal. So if you make them normalized also, then they will become orthonormal. So we will get a set of orthonormal basis function. So by using this LCAO molecular orbital approach, a particular form of the wave equation, okay, using this wave functions, we form this wave function, atomic wave function. We get the wave function for the molecular orbital, and then we can get a wave equation which has a particular form and which is called secular equation. We will see in a while what is that, and that can be developed. So how it can be developed? So the wave equation can be written in an usual way. So by using Schrodinger equation, so H psi equals to E psi. So I can write H psi minus E psi, which is nothing but I can write in this form where both Hamiltonian and energy is used as an operator, and is equals to 0. Okay, so this is something which we are all familiar with. Now LCO expression for the psi, that is the molecular orbital, is now introduced by giving this expression. Okay, so now if I consider only two term LCAO MO, this above equation, that is here, what I get is this, because I am considering this I to be 1 and 2. So I have only two terms. I could consider n terms. So for that I will have like C1 H minus E phi 1 plus C2 then H minus E phi 2, then C3 and so on. But I take the simplest example where only two terms will exist. So as if I have two basis functions, phi 1 and phi 2, and for that I can rewrite this equation as this. Fine. So I term this particular equation to be as A. Now if I multiply this particular equation by phi 1 and integrate over all the spatial coordinates, meaning by over d tau, then what do we get? So what I just said is written here, right? So I multiplied both the sides by phi 1 and then I integrated over d tau. So that will remain equals to 0. Now in this expression, what you can see is that there are several different integrals, because you can separate these different quantities like H minus E. When you expand, then you can get several integrals. So we will use certain notations for simplicity. The notations are H11, which stands for phi I H phi I integrated over d tau, where Hij is the integral which is given as this, where the two wave functions are different, phi I and phi j, and operator remains still the same, Hamiltonian. And then there is another integral which is the integration over d tau for the product of the two functions phi I and phi j, and that is given by this term Sij, and this Sij is known as the overlap integral. So here we explicitly say what are which particular integral is gives what. So this Hii, so it can be H11 or H22, meaning that phi 1 H phi 1 integration over d tau, or phi 2 H phi 2 integration over d tau, that gives the energy of the atomic orbital phi I, because here there is no interaction between two different atomic orbitals, the same atomic orbital for which I have the wave function as phi 1. So that I am considering. So this gives me the energy of the atomic orbital, whereas Hij, that gives me the energy of interaction between pairs of atomic orbitals, which is not too difficult to understand, because I have two different wave functions corresponding to two different atomic orbitals, and they are interacting energetically, and this integral Hij will give me the energy of this particular interaction. And as I said, Sij is called the overlap integral. Okay, so how much the two orbitals overlap will be given by this Sij integral. So now I have the energy equation that I can write in this fashion, right, using those notations. So I've got this particular energy equation considering only by multiplying that secular equation by phi I and integrating. So I could also do the same thing with phi 2. That means I could multiply the secular equation by phi 2 and integrate over all the space, and in that case what I could get, I would get something like this, right. So you can see the similarity between these two equations that we got. Now these two equations, if I put them together, so I have got these two set of equations. Now these two equations form a system of homogeneous linear equations in C1 and C2, which are the coefficients for linear combination. So for this homogeneous linear equations, you can always have the trivial solutions as C1 and C2 both are 0. Now if in order to get non-trivial solution, what you need to have for by Cramer's rule, you should have the determinant of the matrix formed by the coefficients of these C1s and C2s to be equals to 0, right. So then only I will have non-trivial solution, and here again we have this secular equation in form of this determinant. So this is the secular determinant written in terms of this integrals h11 or h12 or and we have a term particularly this S12. So this ES12 that or ES21 that we can get because if you go back and see these integrals here, so you can change interchange the position of phi 1 and E. Okay, so this has nothing to do because it's like just mere scalar quantity. So therefore you have like E and integration of phi 1 phi 2. So therefore you have E S12, right. So in that way you get this term, okay, and the other terms already we have explained. So one can get the values of this H11 or sorry HIIs or HIJs or SIJs. One can also try to estimate or compute, okay, with the help of some sort of approximation, and using that approximation one can solve the secular equation and get the value of E, which is of utmost importance. Now all the integrals that we discussed, right, so like this H11, H12, S12, S21, all these individual integrals, if you have to solve them, be it computationally or some otherwise, this is fairly time consuming. So we need to actually do some approximation so that our job is easier, we can save a lot of time, right? So one of such approximation is Huckel approximation. So this Huckel approximation, I will explain that shortly. This is a very drastic approximation, but this serves our purpose in a pretty good way. Okay, so for us, Huckel approximation will be a pretty valid approximation, and that will help us in various different ways. We will see that soon. So what is this Huckel approximation? So Huckel approximation says that all the Hij's are equal to alpha ij, provided this I equals to j. Okay, so what does that mean? It means that this interaction energy is 0 until and unless this atomic orbital wave functions that we are considering, that's phi I, that is phi 1, phi 2, phi 3. So this interaction energy will be 0 except for the case where this ith and jth orbitals are adjacent to each other. So I have like one orbital, the next orbital, the next orbital, and so on. So this if I consider the first one and the third one, then the interaction energy is assumed to be 0 under Huckel approximation. Okay, otherwise if they are adjacent, they will have a value of alpha ij. Alright, so if I consider a special case when I equals to j, then I have like Hii. So this Hii is alpha, and this alpha is taken to be the 0 of the energy. Okay, so we will talk about that in detail later when we will take particular example and explain that. And the overlap integral is taken to be 0 under Huckel approximation. So with these approximations, we will try to see now that how it simplifies the treatment of a little bit complex problem. So for example, a pi system of the molecule naphthalene. So what we will do, we will use all the p pi orbitals as my basis, and we number this p pi orbitals as is shown here. So here you have a p pi orbital, here you have a p pi orbital. So we have numbered them as 1, 2, 3, 4, 5, 6, 7, 8 and 9, 10, and you see that the numbers are done in a slightly different way. So that is because here we are considering the equivalence of the atoms there. So if I take the this 10 basis functions involving 10 p pi orbitals on the carbon atoms of the naphthalene molecule, and then we do the treatment as I said in last few minutes, then what we can do, we can form ultimately a secular determinant. So in the previous example we said that okay, we chose only two functions, phi 1 and phi 2, so we had a 2 by 2 secular determinant, right? So here we have 10 basis function here, and then ultimately I should get 10 by 10 secular determinant, and then correspondingly I get the secular equation as this. All right. Now there are there is a 3-step procedure for setting up symmetry factored secular equation. So this is like a huge 10 by 10 determinant, which is really kind of scary. So can we bring in symmetry restrictions here and simplify my life? So First, what we do, we use the set of atomic orbitals, as I said, as a basis for a representation of the group, and then we reduce this representation to its reducible components. In the next step, we combine the basis functions here, orbitals, into linear combinations. That means this we form the SALCs by utilizing the projection operator, and then we list all the SALCs so that all those belonging to a given representation occur together in the list. Fine. So we tabulate them, and we will use this list to label the rows and columns of the secular determinant. Only the elements of the secular determinant that lie at the intersection of a row and column belonging to the same irreducible representation can be non-zero, and these non-zero elements will be in blocks along the principal diagonal. So pretty much similar way as we did when we learned about how to diagonalize the matrix by similarity transformation. I am saying it's an analogical, it's similar. So the secular determinant will therefore be symmetry factored. All right. So let's take the example of this particular molecule, naphthalene. So we said that we have 10 p pi orbitals as my basis, right? So the point group of naphthalene is D2H, and here is the character table for this particular point group D2H. Now using the concept of unshifted atom, you should be able to form the representation. Okay. So directly writing the characters, we get the representation as gamma, and it's shown here. So we have the non-zero characters for identity, for C2y, for sigma xy, okay, and rest of the characters are 0. Fine. So what we are supposed to do? We are supposed to reduce it in the next step. So now at the beginning we said that this p pi orbitals corresponding to all 10 carbon atoms of naphthalene, they are not all equivalent, but they are they form some subsets which contains the equivalent the basis functions here. So we have essentially 3 different sets. In the first set we have the p pi orbital comprising function phi 1, phi 4, phi 5, phi 8, and we have another set having phi 2, phi 3, phi 6, phi 7, and the third set contains the phi 9 and phi 10. Now what you can do, you can either form the basis representation as we just said in terms of the gamma right here, or what you can do, you can consider the individual sets, just like the example that we gave in the previous class for PF3. So if you do that, if you take this basis functions as a basis set and then another set, then you form the representation and then reduce to get this irreducible representation. Now whatever way you do, the result should be the same. So what you can do, you can form this way, and altogether you can find out how many irreducible representations, which type of irreducible representations occurring and how many times. You should get the same result if you take the reducible representation comprising the formed by using the basis set having 10 p pi orbitals, you will get the same result. Okay. So what you have here, you have total 2 AU orbitals with 2 orbitals with AU symmetry, 3 orbitals with B1U symmetry, and 2 orbitals with B2G, and 3 orbitals with B3G symmetry. So next is we have to find out the SALCs, right, corresponding to each one of this irreducible representation. So we have AU or B1U and B2G and B3G. So we have learned how to get those, and all of these irreducible representation that we found by reducing this reducible representations formed out of those basis sets, 3 basis sets. Then we form the projection operators for those irreducible representations and find the SALCs that we can form and normalize them. So you get the SALCs using the same concept that we have used earlier. So altogether, out of 10 basis functions, you should get 10 SALCs, and we see that we get 10 SALCs. So SALCs that we got, we are writing in terms of the psi. So psi 1 to psi 10 are our SALCs. Now we can get the secular determinant in terms of blocks, and we get 2 3×3 blocks and 2 2×2 blocks. So essentially we have 2 3×3 determinant and 2 2×2 determinant, and let's start one by one. So B3G had a 3×3 determinant, and we take that and solve the equation, right? So when we write the secular determinant and then the secular equation for say B3G, and you try to solve that, you get the result in terms of the notation that we used under Huckel approximation, that is either alphas or betas. Now I mentioned that alpha is taken to be the energy 0. So what is the energy 0 here? So in case of molecular orbital, when we draw the molecular orbitals, so as a function of energy, so energy follows the vertical direction, and then we have different molecular orbitals formed. So now the energy equals to 0 will lie somewhere where essentially you have the atomic orbitals having their energy. So meaning that there is no interaction between these atomic orbitals at that particular energy. So two atoms are not at all forming a bond. So that energy level is taken as a 0. So and under Huckel approximation, this alpha is taken to be that 0. Okay. So and beta is the unit of energy. So beta will give me 1. So taking those terminologies and S1 2 or S2 1, these are 0 under Huckel approximation, we get the results as H88 equals to alpha, H910 910 is equals to beta, and H810 as root 2 beta. So we can keep going and calculating all the other secular determinants for other irreducible representations, and then put the conditions that is imposed by the Huckel approximation, and you ultimately get the total energies. Okay, so energies corresponding to each irreducible representation, essentially meaning that for say AU you have 2 SALCs, meaning that 2 orbitals will be formed. Okay, so when we solve for the determinants, okay, if it is 2-dimensional you get 2 roots, if it is 3-dimensional you get 3, so you get 2 or 3 different energies, right? So once you solve for all the determinants that you get these energies, and then you have to arrange these energies in an energy scale, right? So here we have done that is after finding this energies corresponding to a particular orbital with a particular symmetry. So then we just arrange this energies. from lower to higher. So energy 0 is here, okay, in the unit of beta, of course. So as you go higher, you have this as negative, because beta itself is negative. Whenever there is an interaction, you get the energy as negative. So when you fill up the molecular orbital that you form, you follow the Hund rule and the exclusion principle. So when you follow the Hund rule and exclusion principle, you should be able to fill out all the electrons into the orbitals. Okay. So with this we will stop today, and we will come back tomorrow with some other applications of this symmetry and group theory that we have learned so far. Till then, thank you so much.